So the previous discussion was focused squarely on identical monomers. What happens if we want to describe the coupling between monomers that are not identical? Just to give you an example for how this might be of interest, what's shown here on the left is a bunch of the tensor elements, the key non-zero tensor elements, the largest, for all 20 common amino acids. And what you see is that, overall, they're pretty similar, especially given the fact that this one has a larger magnitude than the others. These two really are sort of driving them, and there's not a huge disparity across all the different amino acids. But there are some examples where they're really quite different, and those are primarily for the aromatic amino acids. And so if we want to describe a protein that includes, for example, aromatic amino acids, and we want to look at the electronic NV1 transitions from those, how are those influenced by, or how is the coupling influenced by the fact that the individual amino acids are no longer, or should no longer be treated as being identical? This is just one example, but this illustrates a more general effect where you can often describe things that have contributions from multiple monomers, but not identical monomers, or even identical monomers in different environments, and so therefore you want to handle them differently. And so how do we generalize the architecture that we first introduced? And we're going to do that by taking a step back first. And we're talking about something that we glossed over in the previous one. And that was how do you construct the weights on linear combination based on a perturbation theory approach. And the perturbation theory approach is basically going to say that we're going to take the eigenfunctions for the uncoupled system. This would be the energy, the corresponding energy for a wave function describing monomer A, and this would be the energy of the wave function for monomer B. And then we're going to do this in a perturbation way, saying that the total wave function is going to be dominated essentially by those, but with a perturbation given by kappa, where kappa is the coupling term. And so if we then diagonalize this Hamiltonian, we should come up with wave functions that take into account the different contributions of A and B based on the magnitude of the coupling and the relative energies between A and B. So what's kappa? Well, it can really describe any number of interactions. We'll just consider by far the simplest one, which is free space dipole-dipole coupling. So if you've got a permanent dipole for A and a permanent dipole for B, then the energy associated with that dipole-dipole interaction is given by this expression. And that's just based on geometry. As long as you know the relative distances and orientations of those two transition moments, it's fairly straightforward to analytically calculate what kappa should be for any two dissimilar monomers. That's now a 2x2 matrix, and h bar omega A is really the energy of state A, and you've got the energy of state B, and then this energetic coupling term arising, for example, from dipole-dipole coupling. So this is our 2x2. If we diagonalize this and ask what are the eigenvalues are given by these two expressions. And then the corresponding eigenfunctions by the ones down here. And so if we just normalize it, this is just the normalization constant right here, then the wave function is given by omega A, or psi A and psi B with different weightings. So there's a natural relative weighting between A and B in the wave function for the sum state and for the different state. And that just drops naturally out of diagonalization of the Hamiltonian. So now let's ask ourselves, if we now go back and limit and consider the limiting case of omega A, of the energy of omega A and the energy of omega B, the h bar omega A and h bar omega B being equal, so that we have two isoenergetic states, in other words, in the limit of two identical monomers. How does H wash out? Well, if we just plug in where energy A and energy B is equal, then this term goes away, and we're going to take the square root of 2 kappa squared, and what we'll be left with is EA plus EB, which is just 2EA plus 2 kappa times 1/2. So that will just turn out to be E plus kappa and E minus kappa for the two eigenvalues, for the energy of the sum state and the energy of the different state. The corresponding eigenfunctions, just by substitution, give you something that looks like this. And what is this telling you? It's telling you that for the sum state, you've got this 1 over root 2, 1 times psi 1 plus 1 times psi 2.
So this is exactly what we had in the previous expression. And for the different state, we have 1 over square root 2, 1 plus psi 1, minus 1 times psi 2. So it really is the sum and difference between the wave functions that recover, in the limit of identical monomers, that recover the sum and difference states from this more general expression. The big advantage, of course, is that this expression can be used for both identical and dissimilar monomers. Now that's for a dimer. What happens if you want to couple this with a whole bunch of mesomolecules or mesochromophores? In principle, you're going to have coupling between every single one of the monomers with every other single one of the monomers, and that can turn into a pretty hairy matrix, but it's just more math. Just plug it in and chug and you're fine, although often people will assume that these cross terms describing interactions between molecules that are too far apart are typically not as relevant, and so they'll focus primarily on just nearest neighbor interactions, and that makes the diagonalization quite a bit simpler, but it's the same basic idea either way. All right, so just to summarize briefly, we can extend the framework for monomers into multimers by allowing for a Hamiltonian that includes the energy difference for the sum and difference states and the coupling term. This also has an advantage I didn't mention in telling you which of those states, the sum or difference, will be higher or lower in energy, and provides an estimate for the energy gap. So this is a fairly straightforward and general strategy that hopefully will be beneficial.